Okay, folks, this one you'll want to strap in, be ready to hit pause because we're going to fly through all of these tests. Um, it's a weird part of AP Calculus where it's a bunch of little techniques you've got to kind of memorize and learn. And the best way to do that, though, is just to kind of fly through them and just see if you can remember them, and then just keep revisiting them and trying again. But what that means is I want to just lay them out real quick here, and then I'll give you some activities to actually practice and put them into use. So the first one that we're going to look at is the nth term test. And all of these are testing for whether something converges, diverges, both, or something like that. So the nth term test tests for divergence. And in other words, it cannot tell you if something converges. So this only can tell you if something diverges. If it doesn't, if it either says this diverges or we have no idea. That's basically what it's saying. So given a series, and these are all for infinite series, n equals 1 to infinity of a sub n. So this is just given the series of terms that are just arbitrary terms. If the limit as n approaches infinity of a sub n does not equal to 0, then the series diverges. In other words, what this means is if you go out to infinity and you're still adding some number that's not 0, it's going to diverge. And this makes sense because if you've gotten to infinity, then you're going to add an infinite more number of those terms. And so if those infinite terms that you're adding aren't 0, then it's going to diverge. So an example of this would be the series 1 plus 1 plus 1 plus 1 plus 1 all the way out to infinity. Limit as n approaches infinity, obviously the a infinitieth term is going to be 1, but then the infinity plus 1 term is also going to be 1, plus 2 is also going to be 1, and so we're going to constantly be adding an infinite number of 1s, and therefore the sum will go off to infinity. Again, if it does equal 0, it may still diverge, we don't know. So this is only good for proving really quickly and easily if something diverges. The geometric series test we've actually already talked about. This one tests for divergence or convergence. So this, if you have a geometric series, this can tell you whether that geometric series converges or diverges. So this is written a little bit differently than I wrote it before, just to kind of give you some different notation. But we're going to have same idea of basically just some constant to some power times an initial value. Given this series, if the absolute value of r is less than 1, it converges. If the absolute value of r is greater than 1, it diverges or is equal to 1. So as long as you've got a geometric series, it's really easy. You've got a definitive, you just check that r value. If it's less than or equal to 1, converges. If the absolute value is greater than or equal to 1, it diverges. I misspoke there. It's if the absolute value of r is less than 1, it converges. Next, we have the comparison test. This one can also test for convergence and divergence. So this can also tell you both things. It can also have inconclusive results. Actually, no, this does not have inconclusive results as long as you can actually use it. There are situations where you can't use it that I'll explain in a second, but it will always test perfectly for those. So given the series, n equals 1 to infinity with terms an, so they're just arbitrary terms, and the series n equals 1 to infinity of some other set of arbitrary terms. If 0 is less than or equal to a sub n is less than or equal to b sub n for all n greater than some random n, I'll explain this in a second, and the infinite series n equals 1 to infinity of b sub n converges, then a sub n converges. And this one also converges. So what this means is basically if I've got some series, let's imagine graphing the sum of them. Or let me imagine graphing all the points in the series. So we've got some b sub n and we've got some a sub n. So if b sub n is always bigger than a sub n, all the way out to infinity, after a certain point. We only care about after, some random arbitrary point. So they can vary at the beginning, but if eventually b sub n is always bigger than a sub n, and a sub n is always bigger than 0. So in other words, a sub n is sandwiched here between 0 and b. Well, then if b converges, a also has to converge, because basically b will equal some fixed value. So a has to equal some fixed value between 0 and whatever b was. On the flip side, if 0 is less than or equal to b sub n is less than or equal to a sub n for all n greater than some n, and this one diverges, then a sub n also diverges. And this is just the opposite idea of if b sub n goes off to infinity and a sub n is always greater than it, well then it also has to diverge. So this is the same sort of idea we did with the squeeze theorem, but applied to series as opposed to functions. And those are the conditions. So I'll just leave that up there like that for you. Next, the integral test. This one tests for convergence and divergence. Convergence and divergence. And if you're given some series, n equals 1, a sub n, and f of x. So this is just some arbitrary function. If f of x is positive, continuous, and decreasing. Oh, sorry, this shouldn't be a sub n, it should be a function, f of n. So if you've got f of n and f of x where they're the same function, right, because they're both f, just the only difference is for f of n, you're only plugging in every whole number. So this gives you that case. Then the series n equals 1 to infinity of f of n and f of x, and the integral from from n to infinity, both converge or diverge. So they do the same thing. So in other words, this lets you take that series and write it as a function and integrate it. And if the integral is equal to some fixed value, you know that the f of n has to be some fixed value. And the reasoning here is if we imagine some, weird function, If this has a defined area, well then f of n, for plugging in every single number and adding up those, is really just taking a Riemann sum of that function. So in other words, it's just estimating the area under that curve. So if the area under the curve is a defined value, you're going to get a defined estimate. If the area under the curve is infinity, you're going to get infinity for your estimate. So that's the integral test. The ratio test, and we're getting close to being done here. This tests for convergence and divergence. And this is given a situation where P is equal to the limit as n approaches infinity of a sub n plus 1 over a sub n. And the series is n equals 1 to infinity of a sub n. So in other words, the limit as n approaches infinity of the next term divided by the previous term. So a sub n plus 1 is one higher term. A sub n is the lower term. Then the conditions, if 0 is less than or equal to p is less than 1, then the series here converges. If p is greater than 1, then the series diverges. And if p is equal to 1, then it is inconclusive, meaning we can't use the ratio test. Inconclusive. So this is just basically looking at how quickly does the ratio between the current term and the next term change. If it's changing quickly enough, meaning it's getting small quickly enough, that means it's basically forcing it towards 0. If it's not changing, in other words, if the next term is always greater, that's where you get this p is greater than 1, then it obviously has to diverge, because no matter how small your terms are, if they're always getting bigger, you're ultimately going to go off to infinity. If it's equal to 1, then that means it's inconclusive, meaning they might be decreasing at just the right rate to give you a solution, or they might be just not quite right to give you a solution. Then we're going to look at the alternating series test, and this is our last one here, and this tests for convergence only. It can't tell you if a series diverges. So it's basically the opposite of the nth term test. If it'll only tell you this converges or I don't know. So given a series, given an alternating series, and so the way we would write this is the sum from n equals 1 to infinity of -1 to the n, an. So you'll notice that this means every other term will be either -1 to an odd power, meaning it's negative, or -1 to an even power, meaning it's positive. So the conditions are that if the absolute value of a sub n is decreasing, and the limit as n approaches infinity of the absolute value of a sub n is equal to 0, then converges. So again, it can only tell you if something converges. If either of these conditions aren't met, it doesn't tell you anything. But if both these conditions are met, it will tell you that it ultimately converges. So that's looking at all the series tests that we have. It was a bit longer a video, I know here, but I wanted to just run through them. present them and you can come back and check them later. The next activities that you'll do will be practicing these and testing how they work.